here. Everyone's here. Whatever. So yeah, it's either freezing or musty.
Yeah.
You just have to.
Reach me.
So let's say we're coming into land. Who's been doing landings? Yeah. About what airspeed are you coming into land? 65, 70, somewhere in that area. Okay, and that's your indicated airspeed, which has a lot to do with your relative wind, right? So let's say you're coming in to land and you're going 65. And you have a 15 knot direct headwind. If you're going 65 indicated airspeed, you have a 15 knot direct headwind. What would be your ground speed? Roughly about 50. Okay, so you're coming into land, you got like 300 feet or so, and you got that 15 knot headwind, and then all of a sudden it shears to a 10 knot tailwind. What's going to happen to your indicated airspeed?
What?
It's not going to go up. Because we had basically, if we're going 65 and we have 15 knot headwind, 50 knots of that is us moving forward, and 15 knots of it is just the wind that's already there. So if you take away that wind, then all of a sudden we're going 50. And if you add that into a tailwind, all of a sudden our indicated airspeed is more like 40. Does that make sense so far?
Why would that, if it's a tailwind, why would it go down to 40?
So where did I got planes and then they got taken out of here. Hold on.
Understanding why the headwind causes it to go down, that blowing into the tailwind is coming from the back of the. It's not.
Give me a second. There's gonna be a white and blue. Oh, this looks like it's like jump.
That was smart because you grabbed one of those boxes, but they all broke.
Oh yeah. I'm just gonna keep this safe in here.
Yeah.
Keep it secret. Keep it safe. All right, so we have no wind. We have no wind, right? We're on the ground, we have no indicated airspeed. If we are in the air, we're flying at 65 knots, that means our plane producing that thrust is giving us all of that 65 knots indicated airspeed. Okay, so let's say we're on the ground and we just have a 65 knot wind going toward us. Well, we could pull back elevator and we could just hover here because the actual wind is giving us all the energy. We don't need to go forward at all. So we just have this. So if we're going and we have a 15 knot headwind and we're going about 50 knots over the ground, 15 knot headwind going toward us, that adds up to 65 knots of indicated airspeed because it's the speed at which the air is going over our plane. Kind of like if we were in a motorboat going up a river against the current. We're not going very fast relative to the shore, but compared to the water, part of that is the water coming past us, part of it is our boat pushing through it. So now, 65, if we get rid of that wind, we just turn the wind off completely, well now our indicated airspeed would be 50. Does that make sense so far?
Yeah.
15 knots of that relative wind just disappeared. So then we would have an indicated airspeed of 50. And what would I need to do to like maintain my altitude if my indicated airspeed just suddenly dropped?
Pitched in, throttle up or pitch down.
Yeah. You'd have to, well, to maintain my airspeed, I need to pitch down. to maintain my altitude, I need to produce more lift by pitching up, but that's beside the point for right now. So we already know that if we got rid of the wind completely, we'd now be going 50 knots indicated airspeed. Well, then what if we have a tailwind added to that? So we're trying to go through the air to have the air molecules go over the wing to produce lift. Well, if we have wind coming from behind, it's not going to push us like we have a sail or anything. This is going to decrease our relative wind. It's going to decrease our indicated airspeed because, just like, let's say we're on the ground again and we're going to take off in a tailwind and we have a 55 knot tailwind. We can get up to 55 on the ground, but basically the air is going to be still around us. We're catching up to that air. So we're not going to produce any lift until we go much, much faster than that. Makes sense so far? So if we have a tailwind, it's going to subtract from our indicated airspeed. It's going to subtract from that relative wind that we're looking for to produce that lift. So to go back to the example, if we're coming into land at 65 into a 15 knot headwind, and all of a sudden that 15 knot headwind disappears, that brings us down to 50, which is pretty slow. And if that turns into a tailwind, then our relative wind is even less, to 40 then. So we would have to majorly pitch down to regain that airspeed or hit the throttle completely. Did that all make sense? Did you all track with that? Switching from a headwind to a tailwind, it's not always 100% headwind going to 100% tailwind. But it's just a very quick change. So you might come into land and then all of a sudden the wind hits really hard in the corner, you kind of balloon and go up to the right, or it could hit hard from behind and then you just sink a whole bunch. So that's where wind shear is most dangerous, is when you're on a short final, you're setting up to land and all of a sudden your relative wind changes in a very dramatic way. So how do you think, I doubt you've been taught this yet, but using our critical thinking skills, how do you think you might be able to, if you heard on the radio, hey, there's reports of wind shear, 8 knot headwind shearing to a 6 knot tailwind. How do you think you could prepare for that to make sure that you have a safe landing? Just like spitball some ideas.
Add up the difference and then like build that in as a buffer to your airspeed.
Yeah. Yeah, that would work really well. If you want to put it in more general terms, go faster. Another thing you could do is if we need to have some responsiveness, like be prepared to add throttle if you need to, adjust throttle. But if we are in full flaps configuration, that's putting a whole bunch of drag on us. So maybe we would want to land with flaps 2 instead of flaps 3. Or if it's really bad, maybe flaps 1 or no flaps. Being prepared to absolutely, maybe not no flaps because you want to reduce your stall speed, but maybe go in with flaps 2 instead of flaps 3. So that you're not getting any unnecessary drag that would add to the tailwind coming in and then really making you sink. I mean, how many of you have just like had power, came in too high, put power out, and then hit flaps 3? You just sink like a stone. If you try to glide in at like 65, 70 with flaps 3, you just kind of go straight down like this. So if you're going to have a wind shear that's going to shear to a tailwind, well, then maybe you'd want to come in a little faster. Maybe are there any other things you might think of? Let's say you have a really long runway. Is there anything you can do to make sure that you don't come up short?
Go around.
Go around. Hey, that is a fantastic answer. If you don't have a good landing assured, go around. Uh, People try to save landings to impress their CFI or their DPE, which is even worse. They'd rather you show good ADM, good aeronautical decision making, and just go around. But another thing you could do is if you have plenty of room, hey, maybe don't aim for the numbers. Aim a little bit further down just in case you need to land, shorter than you thought. So come in faster. Flaps 2. Don't get low over not a runway. Or if it's really bad, you could always try it if you want, or if you don't feel comfortable trying it, just say, okay, I'm gonna switch to land at Compton or Long Beach or something like that. Just not do it. Wait. Okay.
How can you tell like direction and wind shear is coming? They don't tell you.
Oh, they do. Um, Usually, I don't think they normally don't just say wind shear, maybe in a PIREP or something, but if they say it over the radio, they usually give directions. Has that been your experience, Kate?
I think, yeah, they almost the direction, but also sometimes like the point of the wind shear is it just keeps, it's like not necessarily always an uptick or downtick in like velocity. Sometimes it is just like the shifting direction that
Mhm.
can screw with you. So sometimes
Yeah.
that is the wind shear itself.
You could have the wind could be, a pretty reasonable 8 knots coming from, okay, we're landing at 2.9, right? Wind is 8 knots coming from 260. Is that crosswind coming from the left or the right? From the left. Good. So what if it switched and it was coming from 320? Like that's what the shear is happening. Still mostly a headwind, but now all of a sudden you've been correcting to the left, and then all of a sudden it's to the right, and then you go a little more sideways. Um, I'll be honest, for me, when I hear reports of wind shear that sounds somewhat reasonable like that, and not like a super dangerous wind shear, all I'm thinking is, oh, I gotta be extra prepared and awake. I gotta be on the throttle, I gotta be on my rudders, prepared to go around if I need to, but really I'm just 100% alert and focused on this and ready for basically anything to happen, for me to balloon 200 feet, for me to drop, for me to get pushed over to the side. I'm just like super prepared for anything. Um, yeah, it's not like kind of what you were suggesting of I would add the difference in the wind to my indicated airspeed. It's not exactly a direct formula like that. It's just yeah, kind of being prepared for anything to happen. And one of those ways you can be prepared is come in a little bit faster, have a little bit longer landing distance, be prepared to go around flaps 2 instead of flaps 3. We have a video on microbursts before microbursts. Have you watched this video? No?
I think you skipped a couple slides because you were pushing how much?
No?
No? Never mind.
It's just the keyboard wasn't
Natural
switching
flow.
it.
Progressions.
Okay, microbursts are a type of wind shear. I guess I'll just say that. So Yeah, microbursts are no joke. Um, as you can see, a jet with 3 turbines is not able to counteract the effects of microburst. We would have absolutely no chance. So, what would you experience if you were going to go through a microburst? They mentioned it a little bit in the video, but essentially what a microburst is I wish we would have talked about the phases of a thunderstorm before this. That would have been nice. So essentially, when a thunderstorm is developing, we have a whole bunch of updrafts coming up. It's the vertically developed clouds, moisture is going up, condensing into clouds. Then after that, we have a series of up and down drafts. We have some rain happening. And then after that, basically, there's not enough energy to keep all this moisture in the cloud anymore. All this rain that's kind of coming down and then hitting an updraft and coming back up again. So the cloud just kind of rains its guts out, and that's the death knell of that particular thunderstorm. So, in very severe cases, well, just in normal cases, that just means heavy, heavy rain coming out of the cloud and just rains its guts out. This is a bad marker. In a microburst, we have even more water, more downdrafts coming down. So we have all this coming at a huge velocity. And if there was nothing below it, let's say we were going flying through that at 10,000 feet. We'd be flying along, nothing would happen, and then we hit this, and then all of a sudden we would go down, and then we can come back up because we're just getting those downdrafts. Where it becomes very dangerous, just like that low-level wind shear, this is a type of wind shear, is when we have the ground. As like that guy said in the video, with all those downdrafts coming here, that air, that energy, that wind has to go somewhere. It's not just gonna get absorbed by the ground, it's hitting it. So it's gonna go out here, out here, out here, out here. And on this side, it's gonna go out there. It's gonna come out this direction and that direction. So when it hits the ground, it has to move out laterally. So what would happen if we are flying along in our little sling? We're coming into land, boop, 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 boop. What would happen is we would start noticing what? What would happen? We're on a nice steady approach and we're at 70 knots, indicated airspeed. What would we see? What's the first thing we would notice in our plane? Our indicated airspeed going up. Why?
Because of all the headwind.
Yeah, we're getting a huge headwind. So our indicated airspeed would go up. What would you do if you're under normal circumstances, if you don't know what's going on? Okay, all of a sudden your indicated airspeed is 15 knots more than what you want it to be. What would be your impulse? You want to get back to 70, right? So what would you do?
You pitch up or reduce?
Probably a combination of both. You'd pull some power, pitch up. So that works for, so you like kind of balloon, that works for a while. And now you're going, you have less throttle in and you're pitched up to counteract that. And then all of a sudden you hit these downdrafts. It shears in a downward direction. So now we're slow and pitched up. So we go straight down. And if for some reason, somehow by a miracle, we were able to go full throttle and basically you have to pitch basically straight down. You'd have to outrun this microburst, which isn't going to happen. Let's say by some miracle we were able to do that. Maybe we were high enough up, we were able to do that somehow, and we started recovering, getting out here. Then what would happen? Tailwind. And what happens when you have a tailwind? That we just talked about earlier. I heard a lot of whispers, but no one's saying it out loud.
Relative width.
Yes, so how would we see that in the plane? The indicated airspeed would go down. So yeah, it's
I just got it from earlier, I was still kind of questioning it, I just got it,
yeah,
it just clicked.
good, good. Yeah, so all three parts of this contribute into it's basically impossible to get out. They alluded to this in the video that microbursts, airliners have better technology to be able to detect them. These microbursts only last like 10, 15 minutes. So it's a very short period of time. So if we know that one is happening or is likely to happen, they'll just, people won't fly into that runway for a moment.
Also, this sling shouldn't even be.
Yeah, in a sling, we're gonna be nowhere near these types of conditions. And they're basically landing in a thunderstorm. Even if the mosaic ruling happens, they're like, hey, you're able to go in INC, we're not gonna be anywhere near a thunderstorm.
Ending like.
Yeah, yeah. Yeah. What would happen to a sling and a microburst is like asking, what would happen if we went into a black hole? Oh, you'd be dead long before. Yeah, exactly. You go, that'd be, yeah, you get torn apart, end up smashed into the ground.
The microburst to be there, the rain has to be there too.
Good question. Good question. It's not that one begets the other, but rain falling is going to create some downdraft, and the downdrafts are also not keeping the rain in the sky anymore. Does that make sense? Yeah.
All true. With that being said, though, there are instances that I don't want you to get hung up on this, but it's a test question I've had times now, varying ways where else can a microburst happen? Like, does it have to be while it's raining?
No.
No, it can happen just in like the downdraft stage, or not even just the downdraft stages. There are strong enough downdrafts in general at any like phase of this, you can have a microburst. And then on top of that, I did get asked on a check ride if you can have a clear air microburst, which I'm not gonna lie to you, I did not know the answer based on the way he asked the question. I blindly said yes. He was like, let's go. So the answer is yes to that. You can have a clear air microburst because it's just convective activity without the visible moisture. Is it likely? No, don't get hung up on that. I just want to toss it out there because I was asked this on my actually 2 check rides by the same person. So
Yeah, rain doesn't cause the downdrafts. Having thousands of gallons of water hurtling down toward the ground is going to contribute to it, but it's not what's causing it. And in fact, the downdraft is what's allowing it to not stay in the air anymore. Because when we have updrafts and downdrafts, some of that rain's coming down, but some of it is just kind of circulating in the air.
I also think rain question is they talk about the Virga as being like the visual identification of like a microburst with like the plume at the bottom. Like those are the only 2 ways you can really see it.
Well,
Is that right?
yeah, it is. We'll talk about that. I'm sure Virgo will show up in this week at some point. Yeah, let's go over this. You can notice a microburst from a intense rain shaft. You ever seen rain off in the distance? Yeah, it's right here, what you were saying. Intense rain shaft at the surface, but virga at cloud base and a ring of blowing dust. Virga is like those kind of, it looks like a wispy cloud that's going down. That's virga. Microburst is pretty small, 1 to 2 miles and a depth of a 1,000 feet.
So there's still blowing dust at the surface when it's raining.
If you don't have rain, I suppose.
I feel like it's just like if
Yeah.
there's terrain that's movable underneath you, like you can sometimes see it with like grass or like tall grass or like bush. type of-
Yeah.
If
Yeah,
can
you could
it
see,
going,
you
like-
could maybe see wind going in different directions. If you're flying over a wheat field and all of a sudden you see a big depression and then the wheat going out in all directions, stay away from that. Yeah, that's how crop circles are made. It's short, 5 to 15 minutes, can produce downdrafts of up to 6,000 feet per minute. I mentioned what our best climb rate is earlier. What was our best climb rate at VY? 800 feet per minute. Can we outclimb 6,000 feet per minute downdrafts? Absolutely not. Headwind losses, or gains, 30 to 90 knots. Turbulence, yeah. Oh, and this is kind of the picture I showed, except this is super unrealistic. You would just end up in the ground like right here. Yeah. Good luck with that. And now switching topics to inversions. This is wild. Okay, so we talked about how kind of a standard atmosphere behaves. That the air gets cooler and less dense the higher up you go. And what's a stable lapse rate?
2 degrees.
2 degrees Celsius. So unstable lapse rate, someone other than John, what would that look like?
3 Celsius.
More than 2, certainly. Yeah. That'd be an unstable lapse, right? Inversions kind of have to do with this. It's the other side of things. So this is an anomaly that can occur. It can and does occur a lot in summers here in Los Angeles. You'll be flying in a lot of inversions. So like we said, air rises and expands, temperature decreases. When the temperature of the air rises with altitude, a temperature inversion exists. Okay, so that's just kind of defining it as if you go up in altitude and the temperature gets warmer, that is an inversion. There's shallow layers of smooth, stable air that are relatively close to the ground. You could have an inversion layer at 1,000 feet, could be 2,000-3,000 feet. I did my instruments in last summer, and during your instrument, you're kind of flying a lot at 2,000, 3,000 feet. And at 3,000 feet, you'd be like, okay, this is all right. It's hot. And then you start the approach and be going down through it, and it'd be 70 degrees on the ground and 100 degrees in the air. It's just so hot. The air at the top of the layer acts like a lid. I think Kate mentioned that yesterday. Keeping weather and pollutants trapped below. So normally heat rises. It gets less dense. But if the air is super stable, that warm air kind of keeps everything below. So with an inversion, you get really poor visibility because we don't have any wind taking away the smoke and pollution and dust and all that stuff that's trapped in the air. So you get fog, haze. LA looks like just this big yellow fart all over the place. It's pretty like apocalyptic looking.
Insane description.
A big yellow fart.
Yeah.
Yeah, it was the first thing I thought when I saw it. I was like, it looks like biological warfare. Yeah, diminished visibility. Oh, we're not even gonna talk anymore about inversions. Great. We talked a little bit about humidity, relative humidity, when we were talking about temperature and dew point, what happens when the temperature and dew point get close to each other or meet? Clouds form, visible moisture happens. So if they're far away, you're not going to get visible moisture until it gets cold enough or we get enough moisture so that they do meet. So another way of talking about this is the relative humidity. It's the actual amount of moisture in the air compared to the total amount of moisture the air could hold at that temperature. Yeah, like I said, we mostly look at this comparing the dew points to the temperature. So if the relative humidity is 65%, the air is holding 65% of the total moisture that it is capable of holding. So what kind of would it be warm air or cold air that could hold more moisture? Warm air, yeah. Spread further apart, there's more room for that moisture to fit in there without being kind of compressed out. So 80% humidity on a cold winter day in North Dakota is not going to be holding a whole lot of moisture at all, but a 80% humidity in Costa Rica in summer is going to hold a lot of moisture in the air. We talked about determining cloud bases, so we'll go through this a little quickly again. We use 2.5 degrees, a convergence rate of 2.5 degrees Celsius. So if there is 10 degrees between the temperature and dew point at the surface, 2.5 degrees per 1,000 feet. If we go up 4,000 feet, that's about where the cloud base should be. Is that always accurate? No. Could be 3,000, could be 6,000. But that's generally how it works. Or, I like this, Andrew. Just look at the METAR to find out what the cloud bases are.
That works too.
Fog. What's fog? Can someone tell me what fog is? I'm an alien who's never experienced it. What is fog?
Low level cloud.
Yeah, it's a cloud on the ground. That's a pretty good way of describing it. Cloud on the surface. When the temperature of the air near the ground is cooled to the dew point, or that moisture gets to a place where it is cooled. Basically, we have the same thing as a cloud. Temperature, dew point converge, and we get this visible moisture. And we have a lot of different types of fog, but it's all occurring for the same reasons, just different ways of getting to the same thing where warm, moist air gets cooled and then you get fog. So radiation fog, clear nights, little to no wind. You've seen this in maybe like low level ground, maybe it's kind of like a swampy area at night, that kind of thing. Horror movie type stuff, where there's just like this. I remember being on motorcycle trips at night and we just go down a hill, and in that low level area we go over a bridge over like some swamp area, and it would be like 10 degrees colder just going down 100 feet, and there'd just be this thick layer of fog down there. So low-lying areas, the ground cools rapidly because the ground can't hold on to that moisture. It kind of needs the sun to keep it warm. Ground radiates heat pretty quickly. Water holds on to it. So the ground gets cold quickly, so that warm, moist air that was over the ground now gets really cold, temperature dew point converge, we get radiation fog. The heat from the ground has radiated away, and now temperature dew point can meet, makes fog. Advection fog. Is anyone here familiar with advection fog? Hey, You are? What is advection fog?
Convection fog is the kind of fog we get here all the time, and it ruins all of our fun flying in the mornings and afternoons.
Yeah, marine layer is another term for advection fog. Um, essentially, like I said, the water holds on to heat a little bit more. So we got this warm, we got a whole bunch of water, so we got moisture, we got heat near it. And this warm, moist air is very happy and not going to form any fog right there. But then it gets blown inland where it's colder, and then that temperature dew points converge, and we get fog. And it ruins our day. Yeah. If the winds are super crazy, it's not going to happen. It'll just kind of blow it away. Yeah, above 15 knots, the fog usually lifts and forms a little bit higher. Common in coastal areas, super common here, super common in June.
So dew point is calculated by how much moisture is in the air. That's why when it's cold in the East Coast, it's not.
Yeah, so it's not that it has to get to a specific temperature or a specific dew point for it to happen. We could have, you know, negative 10 degrees Celsius for a temperature and negative 40 for the dew point. Or it could be, 30 degrees Celsius and 25 degrees Celsius for the dew point. Yeah, whether it's hot or cold doesn't really matter. It's just relative to how much water can be held in the air at that temperature. So it's very little when it's cold out. It's a heck of a lot when it's warm out. One time, I was getting ATIS on the way back from Sun and Fun, actually. Maybe you experienced this. Temperature was like, I don't know, 30 degrees, and the dew point was negative 22. It was just like I heard the ATIS and my nose began to bleed immediately. It was like so dry. Upslope fog. Okay, so let's just talk about this. Maybe we can come to this conclusion together. Okay, so we got some warm, moist air over the ground, but we have a hill out in front of us. So here's the hill. Here's our warm, moist air. There we go, something like this. Here's our warm, moist air. This is our like 2,000-foot mountain. Warm, moist air, and we have some wind coming from this direction. The warm, moist air goes, hits this mountain, and starts going up. What's gonna happen? The air is gonna cool. Air is gonna cool. Yeah, because it's gonna be colder up here than it is down here. So we're just moving warm, moist air to a place where it's colder. Have you noticed the theme yet? It's just temperature and dew point, the temperature cooling down to its dew point, and then fog forms. Just different ways that can happen. Push it up a mountain, it'll get colder, and you'll see fog.
So the reason that dew point is changing based on a given day is how dry the air was to begin with.
The reason that the dew point changes is basically how much water has been evaporated into the air.
Already.
Yeah. Steam fog, cold, dry air goes over warm water. So again, cold air, warm water, then you get like moisture going into that cold air, temperature, dew point, converge, you get fog, steam fog. Ice fog is a little bit different. Have any of you been in a place that has like really cold winters, like super cold winters? Yeah, where?
Canada,
Canada,
Boston.
Boston. Yeah, Boston can get pretty cold. It's kind of wet on the East Coast too. It's like it really chills you. I grew up in Minnesota, but lived in New York, and I swear to God, 15 degrees Fahrenheit in New York felt like about -10 in Minnesota because it was so wet and windy that just like ugh.
Yeah, the wind kills.
Yeah. So you maybe have seen this over a frozen lake or pond or something like that. Um, when the temperature is way below freezing and this water vapor goes directly into crystals. So it kind of makes snow fog, if you want to think of it that way. It's got to be way into the negatives. It's the same type of process as radiation fog, but it's got to be really cold to do that. If you watched a horror movie that takes place in like a cold cabin or something like that, there's definitely establishing shot where there's like ice fog over like yeah, it looks like that. You so everyone write these down. These different types of fog. I think I made up an acronym for this. Let me see if I can remember it. It was you and I raps. You, upslope, ice fog, radiation. What was A? Huh?
Advection.
Advection fog. P. Oh, precipitation induced fog, which isn't in there. And what was S? Steam fog. And precipitation induced fog, which isn't in the slides for some reason, is kind of the same thing. Warm rain, raining in a cold place, temperature dew point. They make fog. You and I rap. Okay, so now let's go back to what I would consider the beginning. Clouds. Um, clouds can help you kind of mentally forecast what the weather is going to be like. Looking at clouds can help you determine what's going to happen. Just like fog, we need an adequate amount of water vapor and condensation nuclei. So condensation nuclei is basically just a particulate in the air. It's like dust, something like that. Needs to happen for the moisture to kind of grab onto. When the air cools, reaches saturation point, becomes visible moisture, just like we talked about. And we categorize these by their shape, how high they are in the atmosphere, and what kind of characteristics they have. So classifications of clouds, not types of clouds, but classifications of clouds are low, middle, high, and vertically developed. This was definitely a question I was asked at some point on a phase check or check ride. What are the classifications of clouds, not types? Classifications, low, middle, high, vertically developed. Low clouds, under 6,500 feet AGL. Most of the clouds that we're dealing with on a day-to-day basis. Mainly made of water droplets in depending on the climate, you could get what's called super cooled water droplets. And those are just water droplets that are still in a liquid form, but below freezing, which is kind of counterintuitive. How could it be below freezing and not be frozen? The reason being you need to have that condensation nuclei I talked about. So if it doesn't hit anything, it doesn't get disturbed, it'll stay in a liquid form. And actually, if you look on YouTube, you'll see experiments like that where someone will basically have a super clean environment, freeze a glass or a bowl of water or something, or not freeze it, but chill a glass of water, bowl of water to well below freezing, and then take that bowl and then pour it out, and it'll freeze instantly once it touches something. Yeah, those are super cooled water droplets. Low clouds under 6,500 feet. We have stratus, stratocumulus, and nimbostratus. We haven't defined what those are yet. Or maybe we did. Stratus are like these clouds that we have right now. Thin, not vertically developed, stable. Stratocumulus would be kind of these would be like stratocumulus, kind of a mix between a cumulus cloud and a stratus cloud. Some vertical development, but not much. Pretty uniform. And nimbostratus. Nimbo prefix. Does anyone know what nimbo means?
Precipitation.
Precipitation. These are nimbomaniac clouds. Middle clouds, 6,500 to 20,000 feet. Sometimes they're water, sometimes they're ice crystals, and sometimes they're super cooled water droplets. Which would be the most dangerous for icing, for getting ice on your plane?
The super cold water drop.
Super cooled water droplets, which would be the safest? Like, you're definitely not going to get icing with this, just if you think about it.
Like the water,
There's one other answer.
ice crystals.
Yeah, ice crystals. If it's already frozen, it's not going to freeze to you again. It's just like pick up some snow. It's not going to freeze to anything. It's already frozen, so it's not really a hazard. So really, it's just when water is close to freezing level or below freezing level, then you can get water from the air to freeze onto your plane. But yeah, in the same way that if you're driving through the snow, let's say, the snow is just going to go straight off your windshield, doesn't do anything. But if it's like freezing rain, then you're going to be covered in ice. High clouds are over 20,000 feet. 6,500 feet, 65 to 20,000, over 20,000. Low, middle, high. High clouds are cirrus clouds. Those are just kind of ice crystals. Cirrostratus and cirrocumulus. Yeah, no threat of turbulence, no threat of icing. These are pretty benign, wispy clouds. So if you have trouble finding out like cloud bases and you see clouds that look like this, they're super, super way high up in the air. Clouds with extensive vertical development. These are probably the most important ones because vertically developed clouds are not necessarily 100% of the time linked to thunderstorms, but when you have a thunderstorm, you have vertically developed clouds. Vertically developed meaning we have so much updrafts, that's kind of runaway updraft effect. The atmosphere is so unstable. Okay, so we talked about an unstable atmosphere, and we talked about how when the air is warm and moist, warm air wants to rise. Moist air doesn't want to change temperature. So when it gets to colder and as it goes up in the atmosphere and it gets colder, it's going to stay warm and keep wanting to rise, and it keeps rising and keeps rising until finally it starts forming clouds. And we just have this updraft, 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 goes way up. Do we have? Yeah. We can get vertically developed clouds that basically go up to the jet stream. Like you can have thunderstorms up 40,000 feet or more. But it's that runaway effect from an unstable atmosphere and a lot of moisture. Yeah, they build vertically into towering cumulus, cumulonimbus clouds. Again, what's the difference between cumulus and cumulonimbus?
Rain.
Rain. The base of these clouds form in the low to middle cloud region, but extend way up. Towering cumulus clouds indicate areas of instability. So you're going to have, at the very least, updrafts. At certain stages, you're going to have updrafts and downdrafts. If it's going to rain its guts out in a short period of time, right in front of your runway, maybe that's a microburst. But yeah, very, very unstable. You don't want to be anywhere near it. Yeah, often develop into rainstorms, thunderstorms, large amounts of moisture, unstable air, and it can produce lightning, hail, tornadoes, winds, updrafts and downdrafts, wind shear, night tornadoes. Anything else that I'm missing that we saw on our way to Sun and Fun? Yeah. Hurricanes, possibly? Yeah, lots of negative weather conditions for flying. These are clouds. You can take a look at this picture on your own time if you like. The low level clouds, well, those are lower, and the middle is in the middle, and the upper ones, those are up. High clouds are high. Okay, this is where I would have put first. What is a cumulus cloud? Okay, those are fluffy cotton ball clouds, cumulus clouds. Stratus clouds, thin layer, like that. Cirrus clouds, nice and wispy, like cotton candy. They're made out of water ice, not a huge threat, super high levels. Lenticular clouds, UFO clouds. These basically happen, we talked about mountain waves and the windward and leeward side, what's going to happen. You have updrafts, then you have downdrafts. When you have strong mountain winds, the moisture basically gets trapped in this. Have you ever like seen a fast moving stream or a river that gets that foam churned up, and there'll be like one spot where it just like circles forever and there's just like this chunk of foam right there. Very, very fast, but the foam isn't really moving or doing anything. It's just kind of chilling there. That's what lenticular clouds are doing. The wind is going super fast around it, and it kind of traps it in that oval UFO lens-like lenticular lens-shaped cloud. Looks super benign, but your plane would get messed up next to it. So best to avoid those. Rain-bearing clouds, they look dark like that. Fractal clouds, you don't forget about that. It's not a description that. Have you ever talked to anyone about fractal clouds?
Never once.
Okay. I guess it's a cloud that's broken and not a part of a layer or something. Cumulonimbus, now that's an important one. Thunderstorm clouds. Or severe rain clouds. super vertically developed, intense rains, up and down drafts. I'm not gonna get through all this. Let's take a break anyway. Let's get back at 10:30. Some days we have like pen slides, and other days we have a
Studio today to say that, yeah, that's very.
This is not related to this, I just need to stick with an onion.
I don't like this job. If it's up to me, I'd leave it on.
Not for me, I wouldn't touch it at all.
You get cold?
It's just like, all right, I guess I'm gonna make or something. It's
all moist back.
I'm not so sensitive that I only have a 2-degree temperature window that I can drive in, you know what I mean? Or CG what?
Like the percentage of back like window, is it 20 to 30?
Oh, I don't know. I know what our like CG envelope is, like about 69 to 72, 68 to 72, something like that. Hey. We have a lot of weather to go over today. Last week we had a bunch of days that had slides.
No, Zach is, I'm just sitting in before my class because I have break. So like,
Different
you were-
Goodness.
wait, can I ask you why you're doing? I've never done it that way. I've only like used Mac to explain like how we find our CG window, but you don't need to do it with the weight and balance because it's already pre-calculated. Like the window doesn't change because we have our weight limit already set. Wait, let me see the formula again. Oh, it doesn't just like reverse engineer itself. Oh, well, you might have to convert. Because our CG is in inches, so you might have to convert that to inches because that's in feet. Okay, I'm so curious. I've literally never done that once. I've used Mac to explain it and to sound really smart and to show that I understand how it's calculated, but I've never done anything past that. Cool. Double check that the number, no, the number on our weight and balance is in inches. Our CG is sometimes measured in like centimeters, millimeters though. So yeah, just look for the unit conversion. There we go. Oh yeah. Of course, talk to you later.
Don't start there.
There's this. Like across the street, and like names, Aussies. It's like, they don't find it there. What do I have in there? So it's already, there's stuff in this room that's positive. Or the other one, that's what's been. It's been so awesome. Stick in there. Why is this right now? Price like. Stop it. This is earlier. Yeah, it is something. I believe this specifically, I think it's. Like hours.
Extra credit.
Yeah. You know, I don't feel it until you so soon. I don't know, because at some point, like, I also lost me, I'll feel it. And then I'm sitting there, like, I feel it, yeah. Then I just sit there, then I feel the chill, and I'm sitting back there. Ooh. I'm excited, there's a fraction of flies later on the day, I never fall asleep. I mean, it'll be, I saw it, it's 8, so it doesn't go down to 8:30, but yeah, I know, but it's like from 5:30 to 7:30. Thank you. I also, I think it's great about flashcards that are like private flashcards, I got them years ago, they're like basic. Like, but yeah, I'm like. Searching the sands. How is it? Okay, I need water at home. In the house here of the Earth's surface, once after is real. I was gonna say conversation, yeah, I was like, I would say that. I don't know about all that. I should get that book. And what makes like right now, it's in discussing or basic power. So you can see like way more sure. It was go. Chats or third one. But I think there's the main one, so there's zero stratus, there's stratus, these are those kind of. The little guys. And flow, that makes like that water right here. So she knows a little do this, whatever. Do it form, they just said that. So the one he's like, if you want our compost, no. If you don't. How much? This is, I don't know, so it's not good. What? I'll make them through. That's actually really cute.
Okay, take it back.
And then you can. I know. Oh, and have like little book. Flashcards, but they have diversity, they're mixed locals, and they have like. Yeah. In the dark.
Alright, I mentioned fronts earlier. And we talked about air masses, we got. Cold air masses, warm air masses, and low pressure air masses, high pressure air masses. But they're not stationary, they move. They can move quickly, they can move slowly. But as they move, they're gonna bump up against other unlike air masses. And the border between those two is called a front. Yeah, so the main ones we're gonna talk about are warm fronts, cold fronts, occluded fronts, and stationary fronts. We looked at that Prague chart earlier. These are the symbols that you would see on the Prague chart. Cold looks like little blue icicles, and they point in the direction that it's going. Warm little suns pointing in the direction they're going. Stationary is a combination of both because they're not really moving anywhere. They're kind of sliding alongside each other, but they're not moving from one side or the other. And an occluded front is something else. We'll talk about it later. So a warm front kind of looks like this. It's going to take, we got a cold air mass that's just hanging out over St. Louis, Indianapolis. I mean, this is a big area. Got some cold air hanging out, and the warm air is moving toward the cold air. Which is more dense, warm air or cold air? Cold air is more dense, so the less dense air is going to go over it. That makes sense? So the warm air slides over this warm, less dense air, slides over the cold, more dense air, and that border between, we got warm air, probably with a little bit of moisture in it. Temperature dew point spreads higher. Now we got rubbing up against some cold air. So that border between, we're going to start seeing some clouds because the temperature dew point spread are meeting. And when that happens, we start to get some rain. Nimbostratus. Yeah. Anything else I missed? Yeah, the air, not only the border between the warm and cold air is making that happen, but just as the warm air slides up, kind of like we talked about upslope fog, the warm moist air is getting pushed higher up, which makes it condense. Same thing with this. The warm air is getting pushed up into a higher altitude where it will cool and make clouds, make rain. And let's go back a couple fun facts you need to know. Warm fronts are pretty slow, or usually slower. In weather, there's very little, this will absolutely happen at this point. This is always like that. It's usually a typically type categorization. So most often they move slow, 10, 25 miles an hour, slopes over cold air, make some rain. They can sometimes make thunderstorms, but it's not the most likely condition for thunderstorms. Anything else I want to say in this? Cold fronts are sort of the opposites. So a cold front, we already determined, we agreed, it's canon, that cold air is more dense than warm air. So we got some warm air that's just hanging out, chilling over Columbus. And this warm air is relatively stationary. And now we have this cold air. Is the cold air going to slide up over the warm air? No, because it's heavy, it's more dense, and the warm air is lighter to begin with. So it's just going to slide right underneath it. Think of it like a snowplow or something, where we got this cold front moving and moving pretty quickly, and then we have this less dense air. As this cold front comes in, it's going to push it up. So it kind of wedges its way underneath, shoves all that warm air up, and because it's moving so much faster, and we have, again, warm, moist air getting shot up into higher altitudes, that's going to create vertically developed clouds. It's going to create a lot of updrafts. It's a little more violent. And if we have warm, moist air and updrafts, these are kind of the first ingredients to a thunderstorm. Or, not just because we have the ingredients for the thunderstorm doesn't mean it's always going to happen, but that's generally what it is. Like I said, they go fast. Acts like a snowplow, pushes the warm air up, makes clouds, towering cumulus, thunderstorms, all that jazz. A stationary front is when we have a cold front and a warm front that hit head on, and they're both kind of evenly matched energy wise. So you can imagine if we have cold air here and warm air that's stationary, warm air coming up, it's going to slide over. If we have cold air, stationary warm air, moving cold air, it's going to come and shove this air up. The one that's kind of stationary is not going to put up much of a fight. If we have two of them coming at the same time, head on, well, kind of like that microburst coming down, hitting the ground and spreading out. Well, they don't have anywhere to go. They're evenly matched. They're kind of pushing on each other in the same direction, but they got to go somewhere. So they just kind of slide laterally along in a stationary front. Because it is stationary, it's not moving all that much. So whatever weather conditions you're getting, which is kind of a mixture of cold fronts, warm fronts, sort of a whole mixed bag of everything. If we have a stationary front, it's going to stay rough. Oh, we don't have a picture for it.
There's a flight insight video. That's nice.
Yeah. I don't have time for that. Check out Flight Insight, weather fronts, the only time when you get home. But that stationary front, whatever city is underneath it, usually in these pictures, it's Indianapolis that's just getting absolutely wrecked all the time. Those weather conditions will stay there for a long time until that energy is just completely depleted. It doesn't move that much. You get a cold front. How many of you have ever experienced a thunderstorm where it was like, maybe not sunny skies, but like pretty decent weather, and then all of a sudden the clouds rolled in, got super windy, downpours for about a half hour, and it just leaves? That's a cold front. It's moving pretty fast, so if we ever got thunderstorms here and it was moving north, like we'd have a thunderstorm here in LA at like 11 o'clock. By 11:20, it would be gone, but Orange County, or not Orange County, what's up north of here? Like, I don't know, Altadena, Burbank. Yeah, then they'd be getting it, and it would just pass pretty quickly. Stationary fronts, it's going to be the same weather conditions for a while. We tend to get stationary fronts a lot of times in like the winter, and it'll just drizzle and for like days at a time. Occluding fronts are kind of all of these things put together. So we got cold air and a warm air mass moving. Cold air mass, warm air mass. Warm air mass comes over, it's lighter, it goes up. We know that already, that's a warm front. Well, warm fronts, do they move particularly fast or slow? They move pretty slow. So the slower moving warm front comes up over here, over the cold air. But then right behind it, we got a cold front coming up, and this cold front is plowing through. And do cold fronts move fast or slow typically? They move fast, they catch up to that warm front, and then this cold air mass, the cold fronts, meet. They kind of equalize, but it shoves all of that warm air up off of the ground. So there's not really any indication on the ground of what's going on above. This warm air gets trapped, and you get, oh yeah, Indianapolis getting wrecked. Yeah, it's occluded. What does occluded mean? Like just in general, like the definition of the word. Anyone know what occluded means? Like it means it's hidden. So it's difficult to see or predict. We can see it, however, on a prog chart. We got this cold front, warm front, and they come together. Usually it's purple. I don't know why it looks like this. But they kind of come together like a zipper. And then you get that occluded front. All right, we talked about convective activity. Let's not dwell on it. Yeah, with convective activity, get rain showers, thunderstorms, hail, tornadoes, all that kind of stuff. Thunderstorms, we talked about. Oh, here's a good test question. A thunderstorm is classified as severe when you have either hail 1 inch or greater, winds gusting more than 50 knots, or a tornado. I think tornadoes usually go more than 50 knots as well. Thunderstorms usually happen in the spring and summer, usually in the afternoon and evening hours. On our trip to Florida, they had middle of the night tornadoes, apparently. That's super weird. And another test question. Pilots should stay at least 20 miles away from the outer clouds. Stay away from the thunderstorm, give it a berth of at least 20 nautical miles. If you want to go 30, hey, that sounds good too. Are we going to talk about hail in the next one? No, we're not. One of the reasons that we do that is, remember how I said thunderstorms have up and down drafts? And that water, that moisture is going up and then coming down and then hitting an updraft and coming up again. Well, if we have some condensation nuclei, some dust or something like that, we have that water forming, goes up into a high altitude. What happens when we go up in altitude roughly to the temperature? It goes down. It goes down. So this warm air goes up, freezes, comes back down, maybe melts a little bit more, comes back up, freezes some more, freezes some more, freezes some more, and that's how hail is formed. So this hail gets bigger and bigger and bigger with these updrafts, and then it, sometimes, as this hail is forming, it can go whoop and fly right out of the cloud and then land like 20 miles away. So it doesn't have to be right underneath the system. It can just get shot out and from like 50,000 feet, 30,000 feet, and then just end up hitting your plane 20 miles. So that's one of the reasons that you should give thunderstorms that much of a berth. Yeah, embedded thunderstorms are occluded as well. These storms are in a thick line of clouds. You can't tell that it's a thunderstorm without some kind of outside help. Maybe a weather reporting resource. We have lots of weather resources in our plane that hopefully we'll be talking about later. If we don't by the end of the week, try to remind me. Did you talk about weather resources in the plane? Instrument, like
Yeah.
next rad and stuff?
But not
Yeah. We'll talk about it at some point. But embedded thunderstorms are a hidden line of thunderstorms. And they're difficult to detect with your eyeballs. So people rely on other pilot reports, PIREPs, weather resources inside the plane. ATC can let you know of embedded thunderstorms happening. Squall line. Oh yeah, here we go, Minnesota. We get these types of thunderstorms all the time. They usually, if you see a squall line of thunderstorms, it almost always is going like this, from the northwest toward the southeast, and it just covers the entire the entire continent. I brought up Sun and Fun like 5 times today, but that's what we were encountering where we couldn't go around anything because there was just a wall of thunderstorms. And it wasn't just us. We were hanging out in FBOs with like planes that can pilots for net jets and FlexJet. They can go up 40,000 feet, and they couldn't get around to go anywhere to the East Coast because you gotta go over it or around it, and they couldn't do either because you'd have to go into Canada or like well into the Gulf or Mexico to get around it. So long, long, thin line of thunderstorms. It happens in front of a cold front. Wind shear and the lifting of the atmosphere causes convection in this line. That's what it looks like. Big line across the country. Key takeaway from that. Where do squall lines form? In front of cold fronts. Good. So we need a few different ingredients for a thunderstorm, and this is definitely a question you'll be asked at some point as a pilot. What conditions do you need for a thunderstorm? You need an unstable atmosphere. Ethan, what's an unstable atmosphere?
Like the air just. It's like pressure's like stable.
Yeah, well, an unstable atmosphere is unstable. How would you know that it's unstable? We talked about a standard lapse rate. Does that have something to do with it?
Temperature.
At temperature, no, that's an inversion. So it's just that it gets a lot. Normally it gets colder at like 2 degrees Celsius per 1,000 feet. This would get colder much faster than that, which means anything rising would continue to rise. That would be an unstable atmosphere. We need a lifting mechanism. Usually it's those updrafts. It could be, I guess, terrain could also be a lifting mechanism. Can you think of any other lifting mechanisms? Gotta have a lifting force. You need an unstable atmosphere, lifting force, and moisture. If you don't have moisture, you're maybe have some crazy weather conditions, but it's not going to be a thunderstorm. If you have a lifting mechanism and sufficient moisture, like we have a mountain and we have moist air going up it, we're not going to get a thunderstorm. We'll get some visible moisture. We're not going to have a thunderstorm. We have an unstable atmosphere, lifting mechanism, and moisture. We also might not get a thunderstorm, but those are the ingredients necessary to have them. Sun heats the surface of the earth, warms the air above it. Once it rises, it'll continue to rise with that unstable atmosphere. Remember, moist air hangs on to that heat longer, so it just rises, kind of a runaway effect. As it rises, it transfers heat from the surface to upper levels of the atmosphere. Water vapor it contains begins to cool and forms clouds. Starts with thunderstorms. And I would have started this when we were defining what a thunderstorm is, but thunderstorm has 3 different stages. Cumulus, mature, and dissipating. You will definitely be asked this question at all as well. On your written test, you'll get it asked on your check ride probably, definitely during your phase checks. I always think of it as beginning, middle, and end. But yeah, the developing stage, also known as the cumulus stage, where we have those updrafts. We don't have any downdrafts yet. Updrafts, warm, moist air going up, visible moisture in the form of clouds. Mature stage, we have updrafts and downdrafts. Are we gonna do more? Okay, let's go to it. Okay, and in the developing stage, there's basically no rain. You could have lightning, making these cumulus clouds. The mature stage, middle of the cycle, updrafts feeding the cloud, but also precipitation begins to fall. We get downdrafts, a column there pushing downward and upward. When the downdraft and rain-cooled air spreads out along the ground, it forms a gust front, a line of gusty winds, kind of like we talked about the microburst, it goes down, and then once it hits the ground, it goes out. The mature stage is most likely time for hail, heavy rain, lightning, strong winds, tornadoes. This is the main part of the thunderstorm. I believe it also is the longest lasting part of the thunderstorm. And the dissipating stage is where it rains its guts out. These updrafts are overcome by the downdrafts. Energy is decreasing in the storm, and just all of that suspended precipitation falls to the ground. Rainfall decreases in intensity once it's rained out the bulk of it. You can also get lightning during that. Lightning, bad. It's sky electricity. It can blind you. I remember hear that the pilots that were supposed to drop atomic bombs had to fly with an eye patch. Yeah, there was a time where pilots would have to fly with one eye patch in case an atomic bomb went off and it blinded them, so then they could flip it over to the other side. Same thing if they dropped it, they thought that the pilot, even though they're going the other direction, would still be blinded. So they had to wear one eye patch to keep one good eye and then flip it over once the other eye was absolutely destroyed by it. But yeah, lightning close up can blind you. Yeah, unable to see really anything. How many of you have woken up in the middle of the night, gone to the bathroom, and turned on those super bright fluorescent lights and you can't see shit? Yeah, it's like that, but way worse. Yeah, lightning disrupts radio communications. Yeah, electricity, magnetism, radio frequencies. Yeah, I've never seen it.
Pretty cool.
Actually, let's just we'll pick up tomorrow. Elmo, bring fire. Okay. St. Elmo's fire. I don't think this is it. Airplane. As nuts.
I need to show it to you. We're gonna get video of it.
Yeah. Yeah. The reason that lightning happens is we have a whole bunch of electrical like charges in the air, and then it finds something to discharge that on the ground or in the air. And while we're flying through all of that, then we can get miniature versions of that on the plane. Pretty cool. We're gonna continue with weather tomorrow. We're almost done with this. Oh, we're just going over AWC. Balance these lessons. We're just going over AWC tomorrow. Okay, that's fine. Oh, we'll finish this up tomorrow. And yeah, especially if you don't fly today, study an extra 2 hours. Get ahead on the ground. Say it every day, probably gets obnoxious. But when you don't get your check ride because you didn't have your written test done, I'll rub it in your face and I won't feel good about it. But I will say I told you so. All right, have a good rest of your day. Be superstars.